Probability is used in real life in areas of business, sales, politics, insurance, investments, and testing of new drugs. We think of probability in gambling, but there are many other useful applications. It is useful for students to understand probability in making predictions and then comparing the predictions to the actual outcomes. So probabilities are ratios expressed as fractions, decimals, or percents determined by considering results or outcomes of experiments. Keep in mind, percents are just a decimal written on a different scale. Okay, so when computing probabilities, the results are numbers between 0 and 1 inclusively. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. And we will consider the probability of an event unusual if it is less than 0.05. So, if you're working probability problems and you get an answer that is greater than 1 or less than 0, you know you've done something wrong because of this first note here that probability results will always be numbers between 0 and 1 inclusively. An experiment is an activity whose results can be observed and recorded. Each of the possible results of an experiment is an outcome. For example, if we toss a coin, there are two distinct possible outcomes, heads and tails. A set of all possible outcomes for an experiment is a sample space. The outcomes in the sample space cannot overlap. So, in a single coin toss, the sample space is given by capital S, representing sample space, and head-tail in your sample space. The sample space for rolling a single die are the numbers 1, 2, 3, 4, 5, and 6. And that's your standard 6-sided die. Any subset of a sample space is called an event, and a simple event is an event that cannot be further broken down into simpler components. So consider rolling a single die and getting an outcome of 3. This is a simple event because there is no other way to get a 3. The outcome cannot be broken down into any simpler events. Consider rolling 2 dice and getting an outcome of a sum of 7. This is not a simple event because there are several ways to get a sum of 7. The outcome can be broken down into simpler events where you'd have combinations of 1 and 6, they add to 7, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Those all add to 7. They are your simple events, and you have an outcome of a sum of 7. Now, notice that 1 and 6 and 6 and 1 are considered different simple events. 2 and 5 and 5 and 2, different simple events. Okay, so you would count them all as part of your outcome, or as your set of outcomes for a sum of 7, and you would count them separately. So suppose an experiment consists of drawing 1 slip of paper from a jar containing 12 slips of paper, each with a different month of the year written on it. Find each of the following. So the sample space S for the experiment, so S is equal to, and we're just going to use a set notation, which is opening a brace, and then we'll write all of our 12 months and then close the brace at the end. And we can abbreviate January, February, March, April, May, June, July, August, September, October, November, and December. And then we close our brace. So the event A consisting of outcomes having a month beginning with J. So we're going to find each of the following. The event A consisting of outcomes having a month beginning with J. So our event A consists of January, June, and July. The event B consists of outcomes having the name of a month that has exactly 4 letters. So B, the only months that have exactly 4 letters are June and July. And then the event C consisting of outcomes having a month that begins with M or N. So, months that begin with M or N: March, May, November. Suppose an experiment consists of tossing 2 six-sided dice and figuring the sum of 2 dice. Find each of the following: the number of total outcomes in the sample space. So we can use our fundamental counting principle here. We have 2 events that are happening. We're tossing 2 six-sided die. Or you could think of this as also tossing 1 six-sided die twice. But when you toss it the first time, there's 6 possible outcomes, and you toss it the second time, there's 6 possible outcomes. And 6 times 6 is 36. So we use our fundamental counting principle there. Now it said find the sample space for the experiment. This is a little bit trickier because we need to make sure that we get all 36 events. So we're going to make an addition table for 1 through 6. And once we make our addition table, we'll have all 36 possible outcomes. Now, this is not perfect by any means, but 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. Remember making addition tables back in grade school? Same concept here. 1 plus 4 is 5, 1 plus 5 is 6, 1 plus 6 is 7. So go ahead and finish making that table while I complete the table as well. If you need to pause the video in order to complete it, you can. You'll notice there is a pattern. And hopefully the largest sum that you got was 6 plus 6, which is 12. If you got anything over 12, need to rework that. So the sample space for S consists of these 36 different sums. Because remember it said the number of total outcomes in the sample space is 36, and we're figuring the sum of 2 dice. We do count the ones that give us the same sum as individual simple events. 1 and 3 is different from 3 and 1, and you can see that on the table. For example, if we add 1 and 3, we get 4, but if we add 3 and 1, we get a different 4. So those are different simple events. Now when you're using or finding probability, make sure you use the correct notation. P denotes the probability. A, B, and C, or other capital letters of the alphabet, denote specific events. And we would write P, open parenthesis, A, close parenthesis, and read that P of A, or the probability of A, and that denotes the probability of event A occurring. For example, if we were asked to find the probability of seeing a head when we toss a single coin, we would write the probability of heads is equal to 1/2 because there is one head out of two possible choices. Now, when expressing the value of a probability, either give the exact fraction or decimal or round off final decimal results to 3 significant digits. So make sure you do round correctly. Either write your answer as a fraction or round your results to 3 significant digits. We have the law of large numbers. If an experiment is repeated a large number of times, the relative frequency probability, and remember relative frequency was just the percentage of how many times something occurred, the percentage of the frequency out of the total number of items. And the relative frequency probability of an event tends to approach the actual probability, or what we would call the theoretical probability. So an example of that would be if we were asked to find the probability of seeing a head when we toss a single coin, we would write probability of heads equals to 1/2. However, if we toss the coin 10 times, we will not get exactly 5 heads every time for every 10 tosses. We may get, for example, 4 heads and 6 tails. Therefore, the relative frequency probability would be 4 out of 10, or 2/5. Now, we could toss that coin 10 times again, and maybe we get 5 heads and 5 tails, so the probability of heads in that case would be 1/2. Or we could toss it 10 times again and get the probability of heads to be 3 out of 10 because we got 3 heads and 7 tails. But the law of large numbers says the more times we do that if we toss the coin 10,000 times, we could expect a probability value closer to the actual 1/2 than if we only tossed it 10 times.